Good morning. We are here in FEEM, Fondazione Enrico Mattei, with our seminar with the title is The Evolution of a Matrix Model. So we started 2 years ago, more or less, with building this model. The model of the name is Matrix, is an agent-based model that is started 2 years ago, and we started to build this model related to macroeconomics in order to arrive to a model integrated with climate change, environmental economics, and some issues related to this in the our program. The title is Modeling the Energy Transition. Now today we have a presentation of this evolution of a model with new elements that are added related to climate change, carbon tax, and so on. The two presenters will show you in this next 40 minutes, more or less. After we will have some possibilities from some questions also from online. If you have some questions, you can write in the chat. So I will read this to the two presenters. Now I introduce the two presenters. On my right, Emanuele Ciola, that is a researcher in Fondazione Enrico Mattei and researcher at Università degli Studi di Brescia. And on my left, Enrico Turco, the Fondazione Enrico Mattei and the Università Cattolica di Milano. Now I leave you the floor to the two presenters. Thank you.
Okay, so thank you, Sergio. Thank you, everyone, for being here. So as Sergio said, today we are going to give you some updates about the matrix model. That is the which stands for those of you who don't know, multi-agent model for transition risks, and it's the agent-based integrated assessment model that is that we developed as a MET AB-IAM group. Basically, in today's talk, we're going to focus on, so we're going to split today's talk in two main parts. In the first part, I'm going to briefly present the key findings of the last paper, that is a worm in the matrix, a climate assessment under uncertainty and heterogeneity, which is currently revised and submit, where we introduce the climate version of the matrix model. So building on our previous works where we developed the macroeconomic structure of the model with the energy sector. In this paper, we're going to introduce the climate box in order to analyze the evolution of climate change and the macroeconomic effects. So we're going to give you a sketch of the results. Then in the second part, we're going to present two further extensions that we are currently working on, and we would like to focus more time on this part. The first extension is about the role of demand, in particular the role of green preferences by consumers and firms in driving the low carbon transition. And second extension focus more on the growth and energy transition. In particular, we in this further project, we are going to introduce an endogenous and directed technical change, whereby firms can invest in either green or brown technology depending on the past profitability. So starting with the paper, in this paper we want to address two main issues that, in our view, the standard integrated assessment model are struggling to deal with. That is the issues of uncertainty and heterogeneity. In particular, there is still a high uncertainty about the evolution of climate change and, most importantly, about the related macroeconomic risks. And in our view, this is due to a fundamental disagreement over some modeling assumption within the climate economic literature. And the key controversial points in the standard integrated assessment models relate to three different sources of uncertainty: climate uncertainty, economic, and political uncertainty. I'm going to focus especially on the first one, climate uncertainty, by which we mean not only the inherent uncertainty in the climate system, which is captured by this carbon cycle model that translates CO2 emission into temperature increases, which has course, there's a lot of degree of complexity, and there is a high uncertainty about the climate sensitivity. It is the parameter capturing the change in CO2 emission and temperature, and also on the physical feedback mechanism within the ecosystem that affects the evolution and the transfer of CO2 emission among different parts of the ecosystem. But also, most importantly, uncertainty related to the climate damage function. And this is a modeling tool that economists use to link increase in the emissions to increase in temperature and change in temperature to GDP losses. Okay, and typical standard integrated assessment model adopt an aggregate form, convex function linking change in temperature to GDP losses. And it is argued that this conventional damage function is calibrated to give small damage for small temperature increases, ruling out the possibility of catastrophic events. And as Bob Pindyke, Ilenia's friend, said, this is the most speculative element of the analysis. So we want to further explore the issues within our model. And additionally, related to the heterogeneity issue, there is growing evidence on the importance of the heterogeneous effects of climate change due to the fact that individuals live in areas that are unevenly exposed to adverse climate events, and also firms operate in sectors and in regions that are unevenly exposed to adverse climate events. However, this topic has received little attention in the climate economic literature, at least the modeling literature. This is not surprising because being grounded on the representative agent assumption, which assumes one agent per one sector, standard integrated assessment model cannot capture the distributional impacts of climate change. They can capture the diverse climate impacts across regions, so the regional inequality, but not the diverse climate impacts among individuals within a single region, therefore the socioeconomic inequality. But by accounting for agent heterogeneity, boundary rationality, and decentralized market interaction, agent-based integrated assessment model are seen as a complementary modeling approach to the standard IAM, capable of capturing the role of uncertainty and heterogeneity in the low carbon transition. So what we do in this paper, we develop a climate version of the matrix model based on our previous works, by adding a climate box in order to have a full-fledged agent-based integrated assessment model, which includes, as any integrated assessment model, includes two parts. One is the economic model, that is a macroeconomic multi-sector, multi-agent model calibrated on Euro area data, and a climate module, which includes a carbon cycle and climate damage function. The goal is to analyze the evolution of climate change and its macroeconomic effects using different carbon boxes. We have an agnostic approach about what is the best climate box, including carbon cycle and damage function, to adopt. Therefore, we test the impact of different types of climate box that we found in the literature in order to account for the climate uncertainty due to the modeling assumption related to the functional form and the model parameters of these climate boxes. Then second goal is to compare the effects of homogeneous and heterogeneous climate shocks that the agent-based structure allows to do on the economy to account for the socioeconomic heterogeneity. Furthermore, we within this setting, we conduct a set of climate policy experiments aimed at reducing carbon emission, focusing in this paper on the role of supply side factors, that is the role of carbon tax in creating incentive for firms to invest in cost-effective abatement technologies. Then in the extension that Emmanuel will present, we will see also the role of demand side factors, so green preferences and so on. I will skip this for sake of time. And okay, in this slide you have an overview of the matrix model. In the next slide, I will show you a map with the transaction between sectors. So in this graph, you can see overview of the model, which is, as you can see, characterized by 5 main sectors. On top, we have the household sectors, which includes heterogeneous workers, entrepreneurs, and bankers who receive income in the forms of either wages or dividends. They consume, and they save in the forms of bank deposit. Plus, the owners, that is entrepreneurs and bankers, are called to recapitalize defaulted firms and banks with their own financial wealth. Then corporate sector includes 3 types of firms: energy, capital good, and final good firms, with the interlocked input demand via input-output linkages. And the important thing to keep in mind here is that all firms produce by using a CES technology, and they determine the optimal input demand by minimizing the production cost, given the level of the desired production and input price, where the desired production and prices are adaptively revised according to adapting learning rule with the strategic interaction. Then fossil fuel sector supplies is an exogenous fossil fuel sector which supplies fossil fuel to all firms, and in this version of the model we have only one energy source that is fossil fuel, which is used to generate electricity. This is one of the extension that one of the strict assumptions that we're going to relax in the extension. Then we're quite standard banking sector and the government sector. Here you can see the map of the model setup, emphasizing the market transactions across sectors. So here on the bottom you can see the household sector split in between workers, entrepreneurs, and bankers. You see that workers supply labors to all firms. In the center, you have the corporate sector with energy, capital, and consumption good firms. So in each simulation time step, the sequence of events concerning the corporate sector unfolds in this way. So first, energy firms purchase fossil fuel from the fossil fuel sector, labor, and combined with existing capital stock, they produce and sell energy services to capital and consumption good firms. Then consumption good market opens, so consumption good firms, they also purchase fossil fuel, labor, and energy services, and combined with existing capital stock they produce consumption goods to be sold to all households. Finally, capital good firms, they also purchase fossil fuel, labor, and energy services, and produce capital goods which are sold to energy consumption good firms, and will be available for them in the next period. Here, this is the exogenous fossil fuel sector, banking sectors, including heterogeneous banks collecting deposits from all households, both from all agents, both households and firms, and supply credits to firms which are in need of finance to finance the production, and buy government bonds. Government collects taxes on all agents' income and distribute transfer to low-income individuals. Finally, we have a central bank that sets a interest policy rate according to a standard Taylor rule. This was the macroeconomic structure of the model. Now we're going to see the climate model that we added into this climate version of the matrix model. And in particular, we extend the original setup with 4 flexible climate models, which includes carbon cycle that I already told you, links emissions to emission generated by firms by using fossil fuel to temperature increases. Climate damage, which links temperature increases to microeconomic shocks, that is the climate damage suffered by productive sectors. Then abatement choice, by allowing firms to invest in cost-effective abatement technologies, and climate policy. And in this paper, we focus only on a carbon tax. And as I said, these are flexible models that we add, and we test and compare different types of climate boxes, this carbon cycle, damage function, and abatement function, that we found in the literature in order to construct the baseline integrated version of the matrix model. So starting from the macroeconomic structure, these new red and green boxes highlights the climate boxes. In particular, you have that here on top, there is the climate, so carbon cycle, so sort of atmosphere of the economy that receives emissions coming from firms' production, in particular use of fossil fuel, and gives back damages that hits the productivity of the firms. Then the government sets a carbon tax, so the government collects revenues coming from the carbon tax apply to all firms, and the firms can decide to invest in in emission abatement technology, in cost-effective abatement technology, so in order to reduce the cost of the emission given by the carbon tax. Okay, coming to the simulation, for simulation experiments. First, as I said, we're going to test the impact of different types of carbon cycle. So first, we need to understand how emissions are computed in the model, which is the input of the carbon cycle. So first, as I said, the model is calibrated on the euro area, so it can generate emission for the euro area. This comes from the firm's use of fossil fuels in production. At time 2020, emissions model-generated emissions are aggregated and rescaled to match euro area gigaton of carbon. Then while emission intensity, that is the emission to output ratio, emission intensity, by sectors are calibrated using data on fossil fuel consumption and final emission from natural sectors, mapped into our three sectors: energy, consumption, and capital. While the rest of the world emissions, since we don't model the rest of the world, but we need to model the rest of the world emission to account for the global emission that enters the carbon cycle, affecting the global average temperature. To model them, we follow the stirred literature, with particularly with bootstrap future emission paths, by estimating a via vector autoaggressive model using the log differences of global population, GDP per capita, emission per unit of GDP from 1960 to 2020. Therefore, we can compute the global emissions by summing European model-generated emission and rest of the world emission, which enter the carbon cycle. And we tested these 5 different types of carbon cycle, which differ with respect to the degree of complexity, if you want, from the most simple to most sophisticated one. And in this plot, and in this graph, we can see the first simulation results. On top, you have the model-generated, the simulated real GDP for the euro area. No? On the center, you have the quarterly global emissions in terms of gigaton of carbon per quarter, and up to 2020, you have we have the empirically observed emissions. While from 2020 onwards, we have the model simulated emissions, which combines euro area emission plus the rest of the world emissions. And on the bottom, you have the average temperature, so the projection of the evolution of temperature by using different carbon cycle. You can see that at the end of the century, there's quite significant differences between temperature, average temperature, by using different carbon cycles, ranging from +2 degrees to +4 degrees relative to the first to the pre-industrial era. And but all in all, these temperature projections allow us to cover all the SSP scenarios from 1 to 5 of the IPCC. And okay, given the temperature, so here we have seen the evolution of temperature by adopting different types of carbon cycles. Now we want to see what is the macroeconomic effect of the temperature increase on the economy. And here we're going to use we're going to test different types of damage functions. So to remind you, temperature increase causes macroeconomic shocks, since we have an agent-based micro-founded model. Climate damages affects macroeconomic variables. In particular, we model macroeconomic shocks as a percentage reduction in a firm's total factor productivity. These are the 4 types of climate damage functions that we're going to employ. 3 from Nordhaus, 1 from Lamperti paper. And for each scenario, for each climate scenario, we test, we consider different types of shocks, homogeneous shocks and heterogeneous shocks. Basically, homogeneous shocks, under the homogeneous shock case, all firms experience the same economic loss determined by the damage function. While under the heterogeneous case, each firm has a probability, CD, defined by the damage function, of suffering 100% reduction in labor productivity, meaning that the average damage is the same across scenario, but in the heterogeneous case, some firms are hit by 100%, so are entirely hit by the shock. Some other firms are not hit at all, okay? But the average climate damage is exactly the same. Okay, this plot shows the reports the distribution of the GDP loss at the end of the century, 2100, relative to a no-shock scenario. And that is a distribution of GDP losses across Monte Carlo simulations. And in blue, we have the homogeneous shock. So while in orange is the heterogeneous shocks. Okay, and we assess the impacts of climate change on GDP losses for different scenarios. So in columns, you have the different temperature scenario, from low temperature, middle temperature, and high temperature scenario. No? While in rows, you have different climate damage functions. Okay, so the main takeaway from this plot is that you can see, and you will be able to see it more clearly from the table, that the higher the temperature, the higher the GDP loss, the higher the average GDP loss, meaning that the distribution shifts towards the left. But for the interesting thing is that for low level of temperature, there is no huge difference between heterogeneous and homogeneous shocks. No? But for high level of temperature, under heterogeneous shocks, so the orange distribution. So the orange distribution shifts toward the left, so there's a higher average GDP loss, and the tails become fatter, no? Meaning that a higher likelihood of catastrophic event, higher likelihood of huge GDP loss coming from climate damage. Okay. So in this way, we can say that the heterogeneous climate shock amplify both the magnitude and the volatility of GDP losses resulting from climate change. So yeah, heterogeneous shock amplify the effects of climate change on real GDP. And by looking at this table, which reports more quantitatively only the average for different temperature scenario, for different damage function, and here we report for each scenario both the expected, that is the theoretical damage produced by the damage function, and the realized, the actual GDP loss, both under homogeneous and heterogeneous case. And first of all, we can see that, of course, the higher the temperature, the higher the GDP loss at the end of the century. But the interesting part is that we can see that under heterogeneous shock, the GDP loss is systematically higher than the homogeneous, which is more in line to the expected one. Okay, and so you can see, focusing on the last, the high temperature scenario, the heterogeneous shocks leads to a almost 50% increase in the GDP loss resulting from climate change. This is due to the fact that under homogeneous shocks, all forms are evenly hit by the shock, and they can cut production and optimal input demand in a coordinated manner. So the economy will be able to respond to the shock in a more efficient way. While under heterogeneous shocks, forms are unevenly hit by the shocks, hence they cut, so giving rise to coordination failures and supply chain disruptions that amplify the effect of the shock. So you have some firms that are entirely hit by the shock, so they can produce. Some firms that are not hit by the shock, they would like to produce, they could produce, but they cannot find a supplier. So they will have to downsize the production anyway, because they can produce. And this mechanism further amplify the effects of the shock, which is captured by the agent-based structure of the model. And we can see that coordination failures exacerbate the economic impacts of the shock, leading to a further reduction in GDP and further increase in unemployment rate. This is the cumulative unemployment rate under two scenarios. And this has depressive effects on aggregate demand, leading to not only a lower real wage because of, which is similar across shocks, type of shock, but also different impact on the price. In particular, under heterogeneous shock, you have a lower negative impact on the price, which is driven due to the fact that higher employment leads to nominal wage decrease, which is even stronger than the decrease in price, leading to lower decline in the real wage. Okay, now we'll leave the floor to Emmanuel.
Thank you, Enrico. So now we have a complete framework to use to study how we can go to a low carbon economy. In particular, the first experiment that we perform is the introduction of carbon tax. So the idea is that the government can introduce this carbon tax and adjust it through time, depending on the level of emission in the system. In particular, if the government observed that the level of emissions in the previous period was above a target level of emissions, then it increased the carbon tax. In the opposite case, it decreased the carbon tax. So what we will expect is that the government start to increase the carbon tax up to the point in which the level of emission is essentially to the desired level of emissions, the target level of emissions. In particular, we test 3 emission targets, a reduction in the 25, 50, and 75% of the total emission, respect to the average emissions between 2010 and 2020. The carbon tax at this point gives the incentive to firms to invest in a costly abatement technology. In particular, these technologies is characterized by a marginal abatement cost. The marginal abatement cost essentially describes what is the additional cost of reducing 1 unit of emission in the system. We're starting from the continuous function that we have in the literature. We essentially develop some discrete functions, so divided in different steps, such that the decision of firms to going from one step of emission reduction to another one is essentially a discrete choice. It is not anymore a continuous choice. Moreover, given this marginal abatement potential, firms have 2 different types of incentives to invest in that costly abatement technology. On the one side, there is a cost motive related to the fact that the carbon tax essentially increases the cost of the firm. And if the carbon tax is sufficiently high, then there is the incentive to reduce emission in order to save money to spend more money on the abatement, which to the other side, by reducing emission, it reduces the total abatement, the emission cost due to the tax. To the other side, there is also a profit motive. And as I'm showing you here, so we have the cost-effective motive. So the firm invests in an additional abatement as long as the carbon tax is higher than the marginal abatement cost, which is quite a standard macroeconomic results. And to the other side, we include also an endogenous learning mechanism. So in other words, firms observe competitors. If competitors are more profitable, then at that point, they try to copy the strategy they use in the abatement function. So if the firm observe a competitor which is more profitable and this competitor have a higher level of abatement, then the observing firm will increase the abatement and vice versa. Conversely, if it observe a competitor which is less profitable, it simply explore the surrounding of its current strategy. Notice that the probability of observing a competitors depend on the distance between the 2 firms. So the higher the distance measured in terms of nominal production in the 2 firms, the higher the probability that I will observe a competitor. And this depends also on the parameter omega, which essentially captures the intensity of choice. The higher omega, the lower the probability of observing a firm which is far from me, and when we have omega equal to 0, we have essentially a selection completely at random. Going to the marginal abatement curves that we essentially test, we test 3 different marginal abatement curves characterized by different behavior. The EMF 22, which is characterized, the red line that you can see here, the red line you serve here, which is characterized by high initial abatement cost, and then it flattens. Then we have a completely different function, which is the McKinsey, which have high initial abatement cost, and then it has essentially a vertical asymptote around 80%, and then we have the rise 2008, which is a quasi-linear function which stays between the 2. At this point, as we can see here, for the different rise, EMF 22 and McKinsey, we have the different target of carbon tax for different emission targets. The blue line depicts the 25% reduction in emission, the red line the 50%, and the yellow line the 75% emission reduction. So for higher level of emission reduction, we expect and we found that we have higher carbon taxes. And notice that the 75% emission reduction objective, we have some values of the carbon tax which lies between 100 and 200 euros per ton of CO2, which is quite in line with the recent IPCC results. Moreover, we also include a no abatement situation. We resemble to a situation in which firms have not the opportunity to invest in abatement technology. So the only effect that we have in the system is that the carbon tax, by increasing the cost of fossil fuels, reduce their consumption. Notice that while for the RISE 2008 and the McKinsey, the carbon tax converges to a stable level, for the EMF 22, we have this overshooting. This is due to the high initial cost. Due to the high initial cost, firms tend to postpone the investment in emission reduction, and because of that, the government has to increase the carbon tax to a higher level than the level that will be required in the longer term. And this essentially explains this overshooting in the system. Going to the reduction in the emission level, as you can see, all the scenarios reaches the desired level. For the MF22, we have essentially this overshooting related to, as I said before, to this delay in the adoption of the abatement technology. Notice that for the no abatement scenario, we reach only the 25% reduction scenario, since it would require a really more higher carbon tax in order to reach the 50 and 75% emission reduction. But not last point on this on the impact of the carbon tax is the consumption of fossil fuel. So in this setting, the firms can invest in abatement technology, but they don't stop consuming fossil fuel. They still consume fossil fuel, but they emit less emissions. So what happens is that we'll observe a relatively low reduction in the consumption of fossil fuel compared with at the same time we have also a reduction in the emission. But notice that the delay in the adoption of the abatement technology in the MF22 scenario resemble the situation in which we have a no abatement scenario. So for what happens essentially is that we have that the abatement, the decision, due to the high initial cost, essentially produce a really strong decrease in the consumption of fossil fuel. Things that we do not observe in the other two scenarios. So we have this heterogeneous effect of different abatement technologies, which produce essentially quite different results. Notice that we have found that the higher the reduction in fossil fuel consumption, the lower there is a decrease in the real wage paid to the households. This essentially relates to the fact that due to the higher cost of the carbon tax, this reduces the desired quantity by the firms, which essentially then produce a higher unemployment rate, which then at that point generate a lower wages, real wages in the system. The second extension, which is the first extension, which is also quite the new part of the model, relates to the green preferences. So the idea, we have seen that with a carbon tax, we can promote the investment in a costly abatement technology. But can the preferences of consumers for environmental friendly products promote incentives the investment in less polluting technologies? There have been few attempts to model this demand-induced energy transition. Chan et al. Essentially introduced a disutility of pollution, the labor-leisure decision. Agion et al. 2020 essentially introduced some sort of elasticity of substitution between consumption and emissions, finding a dual effect of competition, because on the one side, competition by reducing prices increases consumption and emission, but to the other side, competition also stimulates technological innovation, and in that side, it produces higher environmental friendliness of products to extract the green rents from the consumers. Notice that here we introduce a given level of green preferences, but the empirical literature shows that there is quite large behavioral barriers to the adoption of low carbon lifestyles, essentially related to the fact that the consumers cannot internalize the benefits coming from a reduction of emission. And to the other side, there are mixed results related to the effect of social interaction. On the one side, the society can promote the environmental friendliness of less, let's say, green people by peer pressure, but to the other side, we can also end up in a situation in which there is locked-in situation, in which the society cannot and do not leave people to adopt different lifestyles. So there are mixed results on the literature on this point. So what we do is, starting from the standard matrix model, we introduce the climate with emissions, and then we introduce the possibility for firms to abate using the DICE 2023 abatement function. So yeah, we updated the technology of abatement. We essentially modify the relation between different firms, allowing for the possibility of considering the amount of emission when they consume, and also we introduce the possibility for consumers to essentially consume also energy and capital goods. Related to what are essentially the modification in the model, we assume that once they set the balance, the budget, consumption budget, consumers decide how much to consume depending on this utility function, which essentially says that there is a trade-off between consumption and the emission and the emitted quantity related to this point, where key essentially capture the elasticity of substitution between the two. Since the abatement cost depends on the consumption of fossil fuel, we adopt different levels, which essentially depend on nu, which is essentially the fossil fuel expenditure over GDP. Lastly, we introduce these green preferences for only households. Then we test also households and firms to see if there are some differences. And then we assess the effects of homophily and heterophily on the firm's abatement decision. So for the reduction, this is the emission reduction in percentage relative to the baseline. The hell blue line represents the amount, the reduction when we have a low green preference, going to the red line, which is essentially when we have a high preference for green products. In the upper panes, we have households and households on the left and households and firms on the right. For omega equal to 10, so firms observe only the competitors which are closest to them, and to the lower panel, we have essentially a situation in which firms observe competitors at random. As you can see on the left pan, we have that the green preferences only for the households can produce only at maximum a reduction in total emission by 40–50%. Conversely, when we introduce also the possibility also for firms to consider the quantity of emission implicit in the input they purchase when they purchase the products, as you can see, which we can reach also the 80% reduction level that we set. So what is one takeaway from these results is that we need absolutely to provide the incentive to firms to invest in abatement in emission reduction, since in this case we observe that consumers alone are not able. In particular, here we have the situation in which we have only household green preferences. This is the level of emission for the different sectors. So the pink one is essentially consumption firm, yellow capital, and the blue one are energy firms. And as you can see, when we have consumer preferences for the households, green preferences also only for the households, the only firms that change their behavior and invest in abatement technology are only consumption good firms, even if energy and capital goods are consumed by the household. Instead, when we introduce also the possibility to firms to essentially internalize this cost, this utility of emissions, as you can see, there is a strong change in the behavior, especially in the energy sector, which is the first one which essentially react quite fast and essentially change quite fastly is policy, going to a low carbon situation in a relatively fast way. Lastly, we want to see what are the incentives for firms to invest in this abatement technology. So as you can see, as you can imagine, there is not the carbon tax, so there is not the cost-effective motive, but only the profit motive, as I showed you before. So for the households, for the capital consumption good firms, here you can see the real net worth for the different scenarios. For essentially the scenario when we have a higher preference for green products, and as you can see, consumption firms invest in the abatement technology because they can extract the rent from the consumers. Conversely, when we look at the energy firms, what happens is that we have completely different results. And this essentially relates to the fact that when consumers and firms start to internalize the cost of emissions, at that point, the energy sector, which is one of the most emitters, at that point must react quite strongly to this result, to this change in the preferences of the consumers. And the competition is so strong that it produces a reduction in the essentially in the relative price relative to the marginal cost of the firms, essentially related to the fact that they cannot charge a higher green rent to the consumers essentially. And then I leave the room for Enrico for the last part.
If you're still alive. Okay, this is going to be, I think, more light, so you can relax. Okay, I'm going to present now the last extension of the model we are currently working on, which deals with the endogenous growth and energy transition, properly speaking. In particular, this extension has two main features. The first feature concerning all sectors. Now, so maybe I didn't stress it before, but so far we assume an exogenous technical change. So the level of productivity of firms increases at an exogenous constant rate. Now, in this extension, we're going to make it endogenous. So we're going to introduce endogenous technical change across all sectors for all firms based on workers' skills accumulation through past work experience. So also called the learning by doing, but at the agent level, okay? And I will show you in a while how. And then second features only applies to the energy sector. In this case, we're going to introduce endogenous and directed technical change by allowing firms to invest in R&D either in brown or green technologies, depending on their past profitability. So in line with the Acemoglu's theory of directed technical change. So the first feature, endogenous technical change across all sectors via learning by doing. So here we assume that since we have also heterogeneous workers, we want to exploit not this feature of the agent-based model, and we assume that workers accumulate skills depending on the amount of hours worked, which in turn depends on their employment status, which can be either full-time, part-time, or unemployed. So S is the level of skills, which we initialize to 1. And then in each time step of the simulation, it can increase at maximum to the G bar G, that is a constant growth rate. But however, the actual growth for worker W depends on her employment status. So which goes from 0 if the agent is unemployed. In this case, the agent will not accumulate any skill. And 1 if the agent is fully employed. In this case, will accumulate a skill according to the G growth rate. Or somewhere in between 0 and 1 if the agent is part-time employed. Then why this matters, because then we can compute the average skill level of workers employed at a given firm, that is S bar, is the average skill level of workers for each firm I, which affects the growth of which, the growth of the average skill level of workers affect the growth in the productivity of the firms, especially on the two primary inputs, that is labor and fossil fuels. So technical change captured by the increase in productivity is endogenously determined by the evolution, the accumulation of worker skills at the firm. Okay. Note that in the we have asymmetric information in the labor market between firms and workers. In particular, firms cannot, we assume at this initial stage, that maybe something that we can work on, but to keep it simple at the initial stage, we assume that firms cannot observe the skill level of workers in advance, but only once they are hired. Okay. Therefore, in the firing, so the worker skills, the skill level of workers enters the firm's employment decision only in the process of firing, meaning that when firms have to cut down production and therefore fire workers, at that point they're going to fire first the low-skilled workers that are typically the part-time workers. Okay. Okay, this is all about the first feature. We have no results so far, so we're still working on the implementation of this. Actually, we had some results, but we didn't report in the slide about the evolution of skilled workers, and we can see that basically the economy experienced a similar growth pattern now in this endogenous version driven by worker skill accumulation to the exogenous one. What second features that I said applies only to the energy sector. Here, basically, we introduce now green and brown technology. So we are going to introduce a diversified energy mix. So far, as I said, there is only one energy source, fossil fuel, used for electricity production. Now we're going to allow firms to have different types of energy sources, other green and green or brown plants. In particular, we assume that energy firms generate electricity using either brown or green plants. So we have heterogeneous firms that can use either brown or green. At the starting of the simulation, there is a small share of green a small share of green firms, while a large share of brown firms to capture the actual composition of electricity market. Then we assume that each plant is characterized by a certain duration, input requirements. Of course, the brown plants requires not only labor and capital, but also fossil fuel, while green plants no. And for different cost structure and productivity. And of course, pollution intensity, since emission depends on fossil fuel, only brown plants by using fossil fuel will generate emission. Then we assume that firms can invest a fraction of past profits in R&D to enhance the productivity of their own plant, and therefore to enhance the competitiveness. No? In fact, this is relevant because in the energy markets, I mean, according to the system marginal price mechanism, we assume that firms submit price and quantity bids, which are then sorted by price in order to construct the energy supply curve. No? And the market price is unique and is determined by the system marginal price, that is the price of the marginal power plants that meets the total demand. And by using this mechanism, we have a interesting market feedback loop, because increase in R&D investments leads to increase in productivity and therefore lower unit cost, and therefore lower bid price, and this leads to a higher likelihood for firms to sell in the energy market because they're positioned first in the supply curve, and therefore lower price, higher profits, and higher profits in turn higher R&D investment and higher productivity, and so on and so forth. So with this type of mechanism, this type of market mechanism in the electricity sector allows to capture this feedback loop, which leads to path dependence situation, as we will see. Then after the firm's plant reach its maximum life cycle, and here we come to the transition part, firms can decide either to reinvest in it, so keeping the same plant, say a brown firm reinvest in the same brown plants, or to switch to a different plant, so from brown to green, incurring in cost of stranded assets, because we assume that not all assets can be used from a brown plant to the green plants. And this switching choice is based on the past average profitability. So firms compare past profitability of brown and green plants, and will decide to switch to a new plant, to a different plants, say from brown to green, depending on the past profitability of these plants, which in turn depends on this mechanism and energy market. So the dynamics can lead to either brown technological lock-in or green transition due to the path dependence inherent into this model dynamics. And within this framework, we can therefore analyze the impact of different types of climate energy innovation policy, carbon tax, R&D subsidy, energy, but also related to the energy market reforms on the likelihood of green transition and associated macro-financial risks. I think that was all. I'm going to skip this because we already bother you enough. Just to sum up the limitations and future work. So the main limitations so far of the matrix model are the two strict assumptions concerning the exogenous technical change and the only one, the presence of only one energy source, this fossil fuel. We are relaxing this assumption, this extension we are working on, by introducing endogenous technical change based on worker scale accumulation, and introducing a properly diversified energy mix to study energy transition. Then we want to also expand climate policy experiments and consider different uses of policy carbon tax revenues. Introduce also endogenous green preferences by focusing on the role of human capital accumulation, social interaction, so to better exploit the network structure of the gene-based model, so to capture the social interaction mechanism influencing the opinions and the preference towards green goods. And finally, maybe in the next chapter, if the project is going to be renewed, we're going to also go forward a global matrix model with different regions, to have a not only multi-structure, multi-agent, but also multi-regional matrix model, and take quite some time and effort. Okay, that was all. Thank you for your attention.
Okay, thank you very much. I have to thank Enrico Emanuele, because it's very difficult to split 2 years in 40 minutes. So yes, it's impossible to explain the extension without explaining also the framework of the model. So I think it was difficult, but they were. And I have to say that the model is also written also with Davide Bazzana, Massimiliano Rizzati at the beginning, also with Andrea Gurgoni at the first year. Okay, now I open to the floor to possible questions. We have 15 minutes or less if you have some questions. Okay. Yeah.
It's more a curiosity, just because we are working with similar stuff. In the technological part, how did you calibrate how did you use data for calibrating the model about green technology versus brown technology? It's just because I'm looking to data for estimating purposes, and we are struggling to how to measure and how to capture properly the green technology stuff.
Facciamo più una domanda. Okay.
I'm not an expert at all, so my question is more curiosity again, and maybe our silly questions is, you were showing until 2100 all your plots, let's say, so there is a meaning to arrive until that period, or you can stop your analysis before, like in 2050, or like closer, instead of going longer. I don't know, I'm not an expert at all, so maybe I'm saying something that is completely wrong. And secondly, when you were showing all the plots, you showed the shaded areas that are the bootstrapping, or what is that shaded area? Because you never mentioned them, and it seems that there are a huge peaks near the end of your analysis. That's something that you should investigate about the confidence, if they're the bootstrapped confidence interval or whatever, because in some plots you have peaks at the end, and why that's happening, and then you're going back again. So that was mainly.
You mean the plots on the first plot that they show on the climate?
Well, all the plots that you
okay.
show, you were having this shaded area. I don't know what does it mean, if this one is just a matter of representing, or if it is bootstrapping or whatever.
Start with these two. Okay. Yeah.
Okay, about about Chiara's question, yeah. So this is the point that we are like struggling on right now, and basically so the calibration strategy is to compare the marginal cost of brown and green plants in order to derive the productivity gap between again brown and green plants that we use to initialize the share of so the green plants. So we have a share of green plants at the beginning of the simulation. We want to initialize green firms differently compared to the brown plants with respect to the productivity by using data on the marginal cost, so the difference in the cost structure between green and brown plants. We are still, I think it is feasible, but we have still to look into the data. We are just at this stage. Okay, for the second question.
Okay, sorry if we have not been so clear. So yes, they are the confidence intervals of 250 bootstrap replications. So we have the 50 and 90% confidence intervals. And indeed, we observe that especially when we perform policy experiments and when we start to reach quite high levels, at that point, the system starts to become quite unstable. And that's explain why we have also this strange behavior, especially at the end, especially when we arrive and when we are close to 2100, that we choose essentially because it's more or less the deadline that all economic climate models set as a target to analyze essentially policies. And yes, that's essentially related to the fact that we have an agent-based model. So there is always that simulation that starts to behaving quite strangely, because at that point, for example, let's say the carbon tax reduces the incentive to produce, but by reducing the incentive to produce at that point, it reduces other forms of other tax revenues, and because of that, it increases the debt. So at that point, it can generate endogenously some situation in which there are quite strange behavior and or exploding behaviors. But in general, as you have seen, they're quite stable. But yes, we are quite aware about this problem, and we should run more and more Monte Carlo at that point to have quite nicely both confident intervals, but still now they're quite good. Okay.
Okay, I also have a couple of questions. I mean, first of all, thanks for the very nice presentation, because I know how hard it is to condensate and compress all the agent-based model into 40 minutes, but you did a great job. Still, I'm quite slow, and so I have some missing pieces probably, and so I want to know some more details about. I think that the first one interesting result that you had was about the effect on the real wages and on the prices on the very long run. It seems that you have an effect on the, I mean, a deflationary effect over the long run. And this, I mean, if I understood it correctly, is due to downward nominal wages, right? Okay, so you don't have any assumption about downward nominal rigidity. Okay, why you decided to not to have it, or I mean, there is a trade-off into that, because there is a huge literature on this topic, and I mean also common sense and empirical evidence suggests that wages are rigid downward. And the second question was about instead the introduction of emissions into the utility function. But the emissions are not at the consumption level, but at the production level, right? So it means that if I understand this correctly, it means that the households know exactly how much emissions are done in order to, I mean, how much each consumption that they do entail in terms of emissions. And so they are able to calculate this and to put it into their utility maximization framework, let's say. So I wonder why you have decided to use this approach rather than, for example, having green products and or by defining goods with a label according to the carbon content, so that the households can change their consumption share accordingly.
So yes, about the first question, we have that the heterogeneous shocks, climate shocks, produce deflationary effects. As you mentioned, this is due to the fact that both types of shocks, homogeneous and heterogeneous, lead to a decline in the real wages. But while I think in the homogeneous case, this is in the homogeneous case, this is due to an increase in the real price. Because the homogeneous climate shocks behave like a conventional supply side shock, leading to a decrease in production, increase in price. In the homogeneous case, we have the pressure effect on price, but the decline in real wages due to the fact that the nominal wage, indeed, due to the further increase in unemployment, decreases. The decrease in the nominal wage is higher than the decrease in the level of price, resulting in a decrease in the real wage. Okay. About the we do have rigidity in the nominal wage setting, downward rigidity. I mean, so why?
Yeah, actually, there is an inside downward rigidity, which essentially relates to the fact that wages are indexed to the inflation. So at that point, you have implicitly no downward rigidity. Okay, at that point, and so you actually are. So we have this type of downward rigidity. Moreover, actually, the wages behavior is aggregate behavior. which we estimate on actual data. So the parameters which govern the behavior, the change in the wages by the households at the aggregate level is essentially estimated on actual data, on actual time series. So we have not considered actually the downward rigidity, but we included this indexation of the wages to the inflation. And regarding to utility and emission, yeah, probably what you're wondering is realistic to assume that consumers can observe the emission intrinsic in the product. Well, this actually opens to an additional problem, which is essentially a signaling problem of signal. And we have not considered that, but we can surely consider this point. Also because that point introduced also additional problems related to how much how can we trust this signal that they provide. So it's for sure it's something that we should work on that. But you see, the biggest problem is essentially related to why there are green preferences, because there are quite large behavioral barriers to the adoption of this type of lifestyle, which are and depends on different things, and most of the time they depends on essentially social pressure, education, and so on. So the individual have quite low power on its preferences on this type on this side.
Thank you.
Okay, I don't know if there are other questions. No, online, no. Other question? No. So everybody is ready for lunch, so we are perfect on time. So we can, I think, we can close here. Thank you very much to all of you for the next seminar. Thank you to Enrico and Emanuele. Thank you.